13.
Jā, es domāju, ka ir laiks sākt lekciju. Šodien ir jūsu presentations of quantum space groups.
Tā būs tikai varbūt otrā daļā. Varbūt, tāpēc, kas ir svarīgāks? Daudz izstāstīt, lai nesaprot, vai izstāstīt mazāk par to, lai saprot?
Protams, mazāk. Vislabāk būtu daudz un lai visu saprot.
Tas ne tikai no manis tā. Man tā liekas. Okay. Very short summary of yesterday's lecture. First of all, when we describe crystalline solid, we need to understand the difference between lattice, which is abstract set of points, cubic lattice, tetragonal lattice, and so on. Each space group consists of part connected with lattice, and the smallest volume in the lattice is primitive unit cell, which is translated over the crystalline space. In this case of perovskite, simple cubic lattice with one parameter and 5 atoms in primitive unit cell lattice. But space group includes also not only lattice, but the division of space, always so-called Wyckoff positions, sets of points connected by symmetry operations. In this case, these sets of points, A, B, C, and so on, and crystalline structure, so lattice, Wyckoff positions, and crystalline structure. This is possibility, there are more than one possibility, where atoms occupy Wyckoff positions. But Wyckoff positions are occupied by atoms according to the chemical formula. So when crystallographers give you information about the structure, crystalline structure, they give you space group. From number of space group, if you have experience, find the type of lattice. It's included in symbol of space group. And then they give you Wyckoff positions occupied by atoms. In this perovskite structure, crystallographers give you space group 2221 and their crystallographic labels PM-3M, this is cubic, and then they give you distribution of 5 primitive unit cell atoms over Wyckoff positions. And as I already told yesterday, there are 2 possibilities, 2 equivalent possibilities to describe this structure. They are equivalent, but be attentive. What is physically defined? The distance between titanium atom and oxygen atom is fixed. This is half of cube H. So, when you put titanium in 1A position, 0, 0, 0, then oxygen has to be in 3B position, and strontium in this one. But when you put titanium in half position, then you need to change this oxygen position. This is important. In other case, you will have a mistake, error. So, what is crystalline structure? Crystalline structure is giving, when you give the space group, in the number of space group you have type of lattice and point symmetry of the whole space group, and then you have distribution of atoms over Wyckoff positions. How many parameters you need to fix when you try to give information about crystalline structure? Lattice parameters and atomic parameters. Lattice parameters depend on the type of lattice. Yesterday I told that cubic lattice has 1 parameter independent of the type of lattice, and tetragonal lattice has 2 parameters, and orthorhombic lattice has 3 parameters, and monoclinic lattice has 4 parameters, and triclinic lattice has 6 parameters, and hexagonal lattice has 2 parameters, and rhombohedral lattice has 2 parameters. So lattice parameters first. Second, depending on which Wyckoff positions are occupied, you have no more parameters, or you need to add parameters if there are free parameters in Wyckoff position. In this case, in both descriptions of perovskite, you have points, Wyckoff points, without any parameters. So, to describe this crystalline structure, it's enough to give only lattice parameter. But this is a well-known perovskite structure, cubic, which is high temperature structure. It is well known that at temperatures less than 110 Kelvin, this structure is distorted. The unit cell is 2 times larger, and in this case you have other space group. This is body-centered. I already told yesterday that F face-centered, Y body-centered, P simple, and base-centered. In this case you have... Oh, excuse me, I forgot the slideshow. Excuse me. So you see, space group of low temperature phase is I4MCN. What it means? It means that this is body-centered, tetragonal lattice, with reflection plane orthogonal to this fourth order axis. And then this is non-symmetric group. I'll speak about in more detail on the rutile example what is non-symmetric. When you have here C or B or A or axis with some small number, not in this case, near the axis order, I'll demonstrate it on rutile, then you will understand what is it. In any case, as you know, especially those who work experimentally, the space group depends on the temperature. And in this case, low temperature phase gives you different space group, different Wyckoff position occupations, and what is interesting that in this case you have no equivalent description of this structure. You see that in this list of Wyckoff positions there are no equivalent positions. So there is only one possibility. More, as I already told yesterday, this Y means that this is body-centered, and crystallographers like to give crystallographic unit cell, which is 2 times larger than primitive one. So, in fact, you have instead of 4, 2, and instead of 8, 4. So it means that you have strontium 2, titanium 2, oxygen 6, because 2 of them here and 4 of them here. Unit cell became 2 times larger, so formally there are now 6 oxygens, but these 6 oxygens are distributed over different Wyckoff positions. In the theory of phase transition, it's possible, but I have no time to explain this, how you connect with phonons in both structures this phase transition. Next one. Next one already we discussed yesterday. This is spheroid structure, very simple. This is face-centered cubic lattice. So crystallographers' multiplicity must be divided by 4. So this is 1A, 1B, or 1B, 1A. These are 2 equivalent descriptions. Face-centered cubic lattice. Next. Already yesterday I talked about this. What is interesting that both spheroid structure and this fluoride structure have the same space group, the same. Face-centered cubic lattice, cubic symmetry, 225, but different chemistry. In one crystal, for one silicon, 1 sulfur, but in calcium fluoride, for 1 calcium, 2 fluorons. Therefore, the occupation is different. In zinc oxide, both occupy position 1A or 1B, the same space group, but different distribution of atoms in these two structures. So if it is understandable, who can tell me how many parameters one has to give for fluoride structure and for spheroid structure? How many parameters? For structure, for crystalline structure. Andrei, one. Because in both cases, the occupied Weikart positions have no free parameters. So it's necessary to give only the cubic lattice parameters, independently on the type of cubic lattice, simple cubic or face-centered cubic. There is one parameter. And now I move to the more unpleasant system. This is rutile, well-known structure. What give crystallographers? They say that there are two formula units, titanium, oxygen 2, in primitive unit cell. So primitive unit cell consists of 2 titanium atoms and 4 oxygen atoms. They say also that this is a tetragonal lattice. This P means that simple tetragonal lattice, so you needn't divide by anything this multiplicity, as the lattice is P. But you see now 4 with this small 2. This is screw axis, when rotation is accompanied by some moving along the axis. On the half of period, in this case, 2 divided by 4. This is half of period. So screw axis is not simple rotation axis, but this is rotation with some translation along the axis. When you have 4th order axis, then you can have 4 with 1, 4 with 2, and 4 with 3. It means 1 4th part of translation, rotation, and 1 4th translation. 2 4th part, 1 half, and so on. And now I'll try to explain, and this is so-called non-symmetric space group, where you have screw axis and the glide planes. What is glide plane? When reflection in the plane is accompanied by some moving on a long translation vector of the lattice. This is glide plane. Screw axis, rotation with some translation along the axis. Glide plane, reflection in the plane with some glide in the plane, along translation vectors. In this case, you have instead M, this N. A, B, C, and N. N means that, we will see it on the structure in more detail, N means that this is glide along diagonal between A and B translation vectors. So let's see on this rutile structure. This is titanium in the center of this tetragonal. This is primitive tetragonal unit cell with 2 formula units. So we need to find 2 titaniums and 4 oxygens. 1 titanium belongs to the whole unit cell. This is 1. And what about these ones? Dima, what do you think? How many of these belong to this unit cell?
Atoms or parameters?
Atoms.
Atoms. I remember 4.
1. We already discussed that when you have some atoms in the corner of unit cell, in the corner, it doesn't matter, cubic unit cell or tetragonal unit cell, these corners belong simultaneously to 8 other unit cells. So to this one belong only 1 of them. Let it be this one. So you have titanium 1, titanium 2. Let this origin of coordinate system is here. This is A position, 0, 0, 0. And then second A position, there are 2 positions. One is 0, 0, 0, and second is corner of cube, half, half, half. And why doesn't matter which corner? I show this corner, but I can show this corner, or this. Why? Because all the corners are connected by translation vectors. So I took this half, half, half. And the Cartesian coordinate system, z-axis vertical, x out of it, and y here. So you have Cartesian system. Now, why this 4 with symbol 2 download? Because let's rotate. This is very important moment. Be attentive. If it will, you will not understand, I'll repeat it. Try to rotate it along fourth order axis over 90 degrees. What happens? This titanium, being at the origin of coordinate system, will not move, because you have fourth order translation axis, which goes through this atom. But what happens with hydrogen, with oxygens? There are 4 oxygens, these 2 and these 2. And Sasha, why these 2 do not belong to the unit cell? I say that there are 4 oxygens in the unit cell. I show these ones along the diagonal and these ones. And I ask why these 2 do not belong to unit cell. Who knows? Alexei knows. Why?
The equivalent by translation.
Of course. This is next unit cell. And this is very important to understand, because chemists like such pictures where all atoms are shown with their neighbors, but you need to understand which atoms belong to the unit cell of the crystal, because in bulk crystal there are many tetragonal unit cells which are repeated by translations. So what happens now? It's very important. What happens when you rotate on 90 degrees around this axis? What happens? Where moves this oxygen? Where it moves? It's difficult. Maybe I will say it moves in the plane and appears not here and not here, but appears up on this oxygen. It means that to restore the symmetry, you need to move by half of translation vector. So rotate by 90 degrees. You are in empty position, but you need to restore the whole structure. You can move or up or down by half of translation vector. See this one. That's why fourth order axis is screw axis, because you rotate and move along the axis. Is it clear? That's very important to understand. And therefore, what happens with this titanium? With this titanium, what happens when you rotate on 90 degrees? What happens with it? It goes to other titanium, which is equivalent by with translation. So this fourth order axis is screw axis, and it is due to oxygens, because oxygens, excuse me, that I show so, these diagonal are crossed, and when you rotate, you are in empty position, and you need to move downstairs or upstairs. Doesn't matter, because this is translation. If it is clear, then I can say that plane M, which is orthogonal to fourth order axis, this is a horizontal plane. In this plane lie, of course, this titanium and these 2 oxygens. And of course, this is simple reflection plane, because when you reflect in this plane, then this diagonal comes to the equivalent. So this is M plane, mirror plane. But one of other planes, there are different planes. One is horizontal plane, two diagonal planes and two diagonal planes, these ones, and two Cartesian planes, which are orthogonal to x and y axes. What happens when you reflect in Cartesian planes? You again, for example, let's consider a plane which is orthogonal to x-axis. Then x-axis comes out, and then you reflect in it. What happens with this oxygen? It goes again to the empty position. Therefore, you need to glide it to other oxygen position, and therefore this is M. As for diagonal planes, you see these diagonal planes, these ones, and these two are in one diagonal plane, and these two are in other diagonal plane, and so it means that this is usual mirror plane. So all the space groups are divided in symmorphic space groups. Those space groups which we considered for preceding three structures are symmorphic. There are no square axes, there are no light planes, and non-symmorphic. There are 230 space groups, and from them 157 are non-symmorphic. What is interesting, and chemists like this, that non-symmorphic can appear only when you have at least two equivalent chemically equivalent atoms in the unit cell. Because what means non-symmorphic? That there is some screw axis or light plane which connects two equivalent atoms. In this case, you see that these oxygens and these oxygens are connected with this screw axis. Is it clear? I was thinking how to explain non-symmorphic, and that I've chosen rutile structure as the best representative of that. This is diamond, again non-symmorphic, but here the screw axis is absent. Here is light plane. Two equivalent, this is other space group. You see F means face-centered cubic. Therefore, instead of this 8, you need to take how much instead of 8? If carbon occupies position 2A, how much carbons are in primitive cell? No, in diamond, how many? 2. But here you can see 8. Why? Because this is face-centered cubic lattice. But crystallographers gives you number of Wyckoff positions in the crystallographic unit cell, not in primitive. And this crystallographic unit cell is 4 times larger. Therefore, 2A and 2B. I already told yesterday that when I write 2A and 2B, and I see crystallograph say, no, you need to write 8. But I say, but nobody who calculates phonons or electron states, nobody will do it with 4. It will consider primitive unit cell with 2 carbon atoms. Nothing more. No 4. No 8. 2 equivalent descriptions, or A or B. What is the problem? You see that here, this is cubic unit cell, because lattice is cubic. But on this figure, how many atoms you see? You see 8. Because this is conventional or crystallographic unit cell, which is 4 times larger. And to primitive unit cell belong only 2 of them. But primitive unit cell is not cubic. This is a unit cell with 3 equal translation vectors, and corner between them 60 degrees. So only 2 atoms belong to this. And why this D? Because it's very simple to understand that as there are 2 carbon atoms in the primitive unit cell, you can interchange them. But what it means? That you introduce some light plane which is not connected with usual rotation, but with some diagonal transformation, because each carbon has in tetrahedral surrounding of nearest neighbors, and it is tetrahedral. But you can interchange carbons, and this adds you additional operation. So this is also non-symmetric group. Corundum is especially difficult. Crystallographers say that this is space group number 167. When they give number, it's definitely known from the list of space groups. There is only one space group with this number. But there, as I already told, for some groups there are two different origin choices, and for rhombohedral groups you have hexagonal and rhombohedral settings. And coordinates depend on setting. And in databases you can find both setting, or one of them. And you need to understand what is setting. So let's consider trigonal crystal system, rhombohedral or trigonal, this is the same. -3, this is third order axis and inversion. And again you see C instead of M. It means that there is blind plane along the C axis. This is primitive unit cell, 4 aluminium atoms and 6 oxygen atoms. And they occupy 4. This is rhombohedral. It's not necessary to divide to anything. 4C, 4. It is C in 4C. And, oh, excuse me, I forgot. But this screen is, Anatoly, for Kamark money, buy some new screen. That one is better, this is worse. So you see that aluminium atoms occupy 4C position, 4, and multiplicity of this is 4, and local symmetry or side symmetry is only rotation around third order lines. But this is 3 parameters along this axis. So don't forget that for structure it's necessary to give it. And oxygen occupied 6E position with local symmetry only C2 or simple rotation on 180, and again 1 parameter in the Wyckoff position. So this is primitive unit cell. Who can say how many parameters one needs to give to describe corundum structure?
4.
2.
4.
4, 2, what else?
3.
3,
No.
5, 7. Rhombohedral lattice is defined by translation vectors, lengths, all of them are equal, so 1, and angle between them, not 90, not 120, not 60 second. So 2 parameters for lattice. And aluminium occupies position with 1 parameter, 3, and oxygen with other parameter, 4. So the corundum structure, not lattice. Yes, sometimes people say crystalline lattice. What they mean? They mean not Bravais lattice, but they mean crystalline lattice. You have to be careful, especially when you read some publications. People sometimes confuse it. Now, more difficult position. Conventional. Some questions? Alexei, some questions? You explain him. Is it clear that 4 parameters, primitive unit cell, consisting of 10 atoms? Non-symmetric space group with rhombohedral lattice. But crystallographers like hexagonal unit cell, not rhombohedral. They think hexagonal is better. Then you have again 2 parameters for lattice, C and A. In the plane, this is C, and these are in plane. Angle is 60 or 120, but length is equal. So the same two parameters, but coordinates of atoms in hexagonal axis are different. You see? Why? Because this is other setting. Don't confuse setting and real size of lattice. In databases, you can find both settings. Of course, I think those who give databases, they understand which setting they use, and therefore they give correct coordinates in the setting which they give. How these settings are connected? With translation of rhombohedral primitive lattice translation vectors are transformed with this matrix. Determinant of it is 3, so conventional unit cell, you can say, call it supercell, is 3 times larger than the primitive. It consists of 30 atoms, 12 aluminium and 18 oxygen. This is conventional, this is primitive. Wurtzit structure, it is very popular. You know that crystals like silicon oxide are layered crystals. There is different interaction inside of the layer and between layers. Inside the layer, the interaction is, we can say, traditional chemical interaction, connected with overlap of electron wave functions, or excuse me, electron wave functions of silicon and oxygen. But between layers, you have weak van der Waals interactions. They are very weak. And they cannot be described by traditional methods of quantum chemistry. But this is other story. Why layered crystals are now very popular? Because layered crystals are so layered that experimentalists sometimes, especially for tungsten disulfide, then they can synthesize one layer, not the whole crystal, but one layer, and it really exists. And it is very interesting because it's very popular in description of nanotubes, where nanotube is received as carbon nanotube, so from layered crystals, by rolling up of this. So this is layered crystal. What give crystallographers? They, as usually, give number of space group. Now we understand that this is hexagonal lattice. 6 order axis, but this is screw axis. Why? Because you have, if it's clear from the picture, you have in one layer 2 planes. One is silicon plane and second is oxygen plane. And these planes are moved relatively to each other. Therefore, this 6 order axis needs to make some translation on the half of this C vector. On the half, it means 6 with index 3, because 3 divided by 6 is half of translation vector. To move from one layer to the second one, you need to make this rotate around the screw axis. Here I try to explain, but maybe we have no time for details, that threefold rotation, you know that if you make rotation around 6 order axis 2 times, what you will receive? You will receive 3 rotation around threefold axis. Yes? Because one half and second half, and 2 times 120 degrees. So you have, as if it would be threefold rotation. But in fact, it is, therefore here on this, in this text, it's explained how this improper rotation, I use screw axis, but sometimes you can find proper and improper rotation. Proper rotation is rotation, usual rotation as in molecules, around the rotation axis, and improper, this is rotation around screw axis. Next one. Again, non-symmetric space. This is other layered crystal, very popular also. Disulfide of tungsten. This is other space group, again with hexagonal lattice. And crystallographers give you two formula units in primitive unit cell, two formula units. It is layered, therefore this is plane of tungstens, and these are two planes of sulfurs. And there are two layers, each of them consists of three planes in primitive unit cell. So the translation vector along that axis. The same idea, as these layers are moved relatively to each other, then the rotation axis is screw axis. This is improper rotation. And here I give the equivalent description. You see that you can change only C and D position. I took it from Psych Bilbao. But C position is here by tungsten atoms, but F position by sulfur atoms. So it means, it's not trivial, that in this structure you can change positions of only tungsten. You can use C or D. But you cannot change the position of sulfur. But we saw in perovskite that when you change strontium and titanium, then you need to change the position of oxygen. Oh, questions, because next concerns the surface modeling. Questions? No questions? No. Okay. Then I will use it is incredible picture. Don't be frightened. I'll show you the whole list of space groups. Now I am on Bilbao crystallographic server. On this Bilbao crystallographic server, you have different blocks: space group symmetry, magnetic symmetry, 1,651 magnetic groups. I will not speak about them. Group-subgroup relations, which are important. And when you consider, for example, some phase transitions, very difficult point, representations of space groups, and some other applications. And as I already told you, there are sub-periodic groups, 2D and 1D. 2D, these are layer groups, and 1D are rod groups. And freeze groups, these are groups of 1D in one dimension. But let's return to space groups. I shall open the whole list of 230 space groups. And I'll try to explain you, but I'm not sure that it's so easy to explain and not so easy to extend also. They are ordered, and each group has its number. And how they are ordered? They are ordered in the order of increasing the symmetry. 1 and 2 groups correspond to triclinic symmetry, when the lattice has 3 different lengths of lattice translations and 3 different angles. The less symmetry position. This is P1 and P minus 1. Why minus 1? Andrei, you can explain why minus 1 also exists. 1 is first order axis. 1 minus 1 exists.
Inversion sign inversion.
Yes, but why? It must be in the lattice, but it can be absent in the group. Because this is 3-dimensional lattice. And it means that any translation vector has to have minus translation vector. In other case, you will not have translation group. And therefore, there are 2 point groups. One consists of, let's see, Wyckoff positions. Only one Wyckoff position, X, Y, Z, with side symmetry 1, 1A. No symmetry. And second, only, Alexei, this is, I think, a space group of your, remind me, what is the name of your crystal?
Copper molybdenum.
Copper molybdenum. Yes. He has crystals with this symmetry. And who can understand? Maybe Alexei himself can explain why there are so many Wyckoff positions with halves, 0, 0, 0, 0, 0, half, and so on. And no lattice Wyckoff positions with 2 parameters, with 1 parameters, only with 3. Can you understand this? Because, very simple. Minus 1, this is simple inversion. If you take 0, 0, half, then minus 1 gives you 0, 0, minus half. But half and minus half are connected by translation vector. And the same with any number of halves in the ordinals. So these Wyckoff positions are not equivalent. But each of them consists of 1 point. But why? Here 2. Because inversion. 1 is some general point X, Y, Z, and second is received by inversion. So you see that lattice is triclinic, but point group can be C1, 1 first order axis, or inversion. Inversion must be in lattice, and this is space groups with inversion. Let's move further. So triclinic system is exhausted. Next. Now comes monoclinic. I remind that monoclinic system has the following. One translation vector is orthogonal to the plane of 2 others. The angle between 2 others and plane is arbitrary. So one parameter of this monoclinic lattice is these angles. And lengths of all 3 translation vectors are different. So you have 3 parameters for lengths. In general, you have for monoclinic lattice, only for lattice, you have 4 parameters. 3 lengths and angle between them. And now begins jokes of crystallographers. Unique axis B, unique axis C, and so on. Because you understand that this axis, which is orthogonal to the plane, this translation, which is orthogonal to the plane of 2 other vectors, it can be B or C or even A. I don't know why they do not use A. They use B and C. And let's see what is the difference. What is this space group? It is simple monoclinic lattice, simple monoclinic P, because as I showed you yesterday, there is also base-centered monoclinic C. So simple monoclinic. And simple monoclinic lattice, unique axis B and unique axis C. Let's see what is the difference. In both cases, you have second order rotation axis. What it means, this B? it means that this y is arbitrary. They say a along x, y along b, and z along c. So this is x is b. And you have all Wyckoff positions for this group. And now let's see unique axis C. In this case, this arbitrary coordinate is it seen? Because I forgot always the second picture. Is it necessary to show? Or it is seen? That screen is better. Okay. Dima, you can help me because I cannot do simultaneously. Show, please, the same from side. Unique axis C. You have to be careful because when you use for your investigation monoclinic system, Alexei, you used monoclinic system as you taught many years ago. You had to be very careful because the translation vectors are different lengths, and therefore, depending on the b-axis or c-axis, you need to take different translation vectors from database.
Why?
By positions, yes. And now choose it. Choose it, no. Choose it. Choose. Okay. What happens now? Now you have monoclinic lattices, space groups from number 3 till number 15. All of them are monoclinic. But from number 3 till number 7, these are simple monoclinic lattice without any C. And from 8 till 15, base-centered monoclinic lattice. Is it necessary to show a picture of Bravais lattices or not? Maybe it's necessary to remind you. I'll find in my presentation.
Possible full presentation.
Yes.
One screen and
Where is it? Where is it? I don't find it. Just a moment.
point groups.
No, here. We consider triclinic lattice with 6 parameters, and now we consider space groups with monoclinic lattice, centered or simple. So you see that ordering of space groups is made over types of lattices, moving from the simplest one to the highest. The highest will be cubic. Now, orthorhombic. Orthorhombic.
You can show another screen because this picture is available.
Sorry?
You can use this screen to comment Bravais lattice and show crystal database.
Okay.
Another.
Orthorhombic lattices, these ones. You see that here you have 4 of them. Simple, body-centered, base-centered, body-centered, and face-centered. For each type of lattices, you have different points of groups, and therefore you have more orthorhombic space groups with 4 types of lattices. When that lattice type changes, of course, the space group itself also changes, and therefore we will see now how many space groups you have with orthorhombic lattices. From 16 till 74. 4 types of lattices. For each type of lattice, different possibilities for point group. All of them have different, both symmetric and non-symmetric. And in non-symmetric, two origin choices. So you see that there are many orthorhombic space groups. I don't know, is it really that majority of crystals have orthorhombic system? I'm not sure. I've seen, I think, some time ago in somewhere in paper that majority of crystals have cubic system, but I'm not sure. Anatoly, I think I'm tired, and I think they are also.
I have a question. What is A? C is base center A?
A is based on A. You have three translation vectors, A, B, C. Orthorhombic centered has base centered can have this node on A, B, and C. It is not so easy to explain the whole table, but as you see, I try to explain you principles. That principle is you are moving over the lattice type, Bravais lattice types. For each lattice type, you have different point groups, including both symmetric and non-symmetric. And it was Fedorov, Russian crystallographer, who was first who announced 230 space groups. He analyzed all the possibilities which appear for all the possible lattices. But second, as I understand, was Schoenflies, Germany. And who was the first? It's discussed. Okay, great.
One additional question. You see the table, and told we start with group number 20 something, and the last one is 74. How to see from the table what this is cubic or orthorhombic? How to see from symbols?
It's very simple, because in orthorhombic you can have also some planes, reflection planes, toward the axis and reflection planes. And in monoclinic you have none of them, only orthogonal. But in orthorhombic you have reflection planes going through the axis. The best would be, Dima, if I would have for all the space groups structures, but it's impossible.